Welcome to AI Paper Slop. Today we are looking at Wan-Streamer v0.3 from the Wan team at Alibaba Group. So if you've been building real-time AI avatars, we've basically just been making glorified Zoom filters.
Right, just agents permanently stuck in an idle loop.
Exactly, nodding and lip-syncing to a text-to-speech engine. But today we are breaking entirely out of that box. The researchers at Alibaba have completely refactored the underlying math of native streaming video generation.
They really have. They stepped away from just treating it as a talking head.
Right. They decomposed the real-time interaction into a shockingly simple equation, which is just video equals world plus event stream. The world is the persistent, stable context, the room layout, the subject identity, ambient acoustics.
And the event stream is everything that changes in real time within that world, like speech or physical movement.
Exactly. This decomposition creates this massive, general-purpose pre-training objective. By using a vision language action, or, a VLA-like process, the model continuously maps incoming user streams into speech, interleaved with open vocabulary behavior directives.
It's generating dynamic physical actions on the fly.
Yeah, and the kicker for all the systems engineers listening, it does this while maintaining the extreme operating specs of v0.2. We are talking 640 by 368 video at 25 frames per second with only a roughly 200 millisecond model-side latency.
Which is just wild for those specs.
Right.
I mean, it completely redefines the baseline competence we should expect from a video generation model.
Yeah, because if you look at versions 0.1 and 0.2, the training objective was incredibly narrow, right?
Oh, absolutely. It was strictly tied to a singular target application, just a conversational agent reacting to you on a screen. You're fundamentally optimizing for a highly specific static interface.
Right, which puts a hard ceiling on physical embodiment. An agent can't walk across a room or grab an object if it only knows how to modulate facial key points.
Exactly. So with v.3, the Wan team stepped back to address a much more foundational problem in continuous generation. They focus on the core capability required to stream video interactively, regardless of the framing.
Let's unpack the formal separation of variables they use to solve this. Like, how does the pre-training data actually define the world versus the event stream?
So mathematically, the world is represented as big W. And think of W as an inferred, highly flexible, structured record.
It's not just a static image prompt, right?
No, not at all. W contains a visual setting, the persistent spatial layout, character identities, and this is crucial for a full-duplex system, the acoustic context.
Oh, right. So ambient sound profiles and specific voice characteristics are durable states held within W.
Exactly. And then we have the event, represented as EEC. The event is a time-localized record of change. It's the delta. It captures exactly what is happening dynamically right now within that durable state of W.
To ground this practically for you, the paper provides two really specific data examples used to pre-train this. The first one is entirely synthetic, almost like parsing a clip from a Grand Theft Auto gameplay dataset.
Yeah, that first example is super clean.
Right. So World 1 is described in the data as a suburban daytime neighborhood with asphalt roads. The character is a humanoid robot in a white and gray armored suit with glowing red lights.
And that entire description forms your static world context, big W.
Got it. Once that state is established, the event stream maps the continuous physical changes over time, running on a sidewalk, turning right, opening a car door, and driving straight.
And the contrast with their second example is so important because it moves from that clean synthetic environment into a really noisy real-world distribution.
Right. World 2 is an outdoor dirt poultry pen, I think.
Yeah, with a green awning. The character is a middle-aged blonde woman in a brown hat. But the durable acoustic context of W here includes the constant chaotic clucking of chickens and roosters.
That's a lot of background noise to maintain.
It is. And the time-aligned event stream for this clip tracks highly complex motor actions. She gestures to the camera, walks to a coop, grabs a white bucket, scoops feed, and actually speaks the words. So basically, this is the commercial crumble.
Looking at how this data is structured, it is fundamentally identical to a video game engine architecture.
It really is, yeah.
From an ML engineering perspective, loading W is exactly like initializing a level in Unreal Engine. You load the environment assets, bake the lighting maps, and W just acts as your pre-filled KV cache of the level geometry.
Right. Once those assets are loaded, the engine doesn't waste compute re-rendering static trees every frame.
Exactly. It spends compute exclusively rendering the dynamic loop of player inputs and physics, which is the event stream. They basically forced a massive transformer to learn the architectural efficiency pattern of a real-time rendering engine.
And formulating it through that lens unlocks a massively scalable pre-training task. You can take almost any natural video on the internet and factor it into a persistent world and a stream of localized events.
So you aren't bottlenecked by needing specialized, high-quality conversational data sets anymore.
Exactly. You ingest massive, diverse corpora to teach the transformer one generalized physics lesson given a static world and an incoming multimodal input. How does that world stream forward plausibly into the next frame?
So how does that generalized physics lesson translate into the actual streaming factorization, like equation 3 in the paper?
So equation 3 defines a conditional probability that drives the whole system. The model predicts the next event, eq, but not in a vacuum.
Yep.
It predicts it based on 3 distinct conditions.
The persistent world W, the history of past events, and the user's streaming input, right?
Yes. So conditioned on the established world, the model continuously maps the incoming user, stream text, audio, or video into an ongoing sequence of plausible next events.
And the paper describes this as a vision language action, or VLA-like process.
Right. VLA is a framework we usually see strictly in embodied robotics, where models ingest vision and language and output physical motor actions for servos.
But here, the actions are the language form speech and the behavior directives driving the video generation.
Exactly. The model learns the causal dynamics of how scenes naturally evolve. If the incoming user audio contains a sudden loud crash, the VLA mapping learns the next probable event, eq, is the character flinching or turning toward the sound.
But wait, mathematically, that sounds way too clean. The real world isn't just a neat single-file line of events.
Oh, definitely not.
You have a character walking, talking, and a dog barking in the background at the exact same millisecond. If we are treating this as a sequential token stream, predicting eq after eq, how does the transformer avoid bottlenecking on simultaneous physical events? Text records are inherently rigid.
The Wan team anticipated that exact bottleneck. The event records aren't strictly sequential in a one-thing-at-a-time sense. An event, eq, is bound to a specific active interval, denoted mathematically as talk.
Oh, okay. So to handle overlapping changes, it simply generates multiple concurrent records within the same talk interval.
Yes, exactly. Multiple eq records share the exact same timestamp slice in the causal stream.
And what about environmental changes not tied to the main character, like the barking dog?
They utilize explicit no-character markers. An event is either associated with a specific character ID initialized in W, or it gets a no-character marker designating it as an environmental occurrence.
That makes total sense. So with this robust pre-training objective, we need to bridge the gap to the actual downstream task. We're executing real-time, sub-second audio-visual interaction. How does this physically instantiate as an improvement over versions 1.1 and 0.2?
Well, the jump becomes clear when you look at the narrow output space of the older versions. Their behavior channel was severely constrained to speech and implicit visible listening.
Essentially just an idle animation loop.
Right. The agent could nod, maintain natural eye contact, produce micro-expressions, and lip sync, but it could not break out of that rigid spatial positioning.
And Wan-Streamer v0.3 shatters that constraint by introducing open vocabulary behavior driven by natural language?
Yes. Instead of relying on an implicit idle state, the agent's physical response is explicitly structured using a role-play chat format.
The model's generated language stream actually natively interleaves the spoken words with parenthesized behavior directives, right?
Exactly. So the output token stream might read, open parenthesis, takes a sip of water, close parenthesis, thanks for the reminder.
Or for a more complex spatial interaction, they show an example like reaches into the grass and picks up a green leaf. Look what I found covers mouth in surprise. I did not expect that.
And the implications for grounding here are massive for agentic AI.
Because the action space isn't limited to a hard-coded fixed vocabulary like WASD input commands.
Right. The agent can perform highly situated actions grounded entirely in its pre-configured W context. If the world initialization includes a red coffee mug on a mahogany desk, the natural language directive can dictate interacting with that specific mug.
From a systems architecture standpoint, interleaving these behavior directives directly into the speech token stream solves one of the hardest problems in multimodal generation synchronization.
Because the physical actions and the spoken words share a single unified token stream, the timing, the sequence ordering, and the interleaving are all learned jointly during pre-training.
So you completely eliminate the need for a clunky external schedule controller.
Exactly.
In older pipelines, you have an LLM generating text, passing it to a TTS engine, and then a separate orchestrator API desperately trying to sync the waveforms with a separate video API. Here, the model natively predicts that the acoustic sound of a gasp happens concurrently with rendering the hand covering the mouth.
The block causal attention mechanism handles the cross-modal alignment intrinsically.
Yeah.
But there is a massive elephant in the room here regarding compute.
Right, because generating open vocabulary video where a character physically manipulates their environment based on real-time text on the fly, usually that continuous latent generation completely crushes your latency budget.
Rendering complex dynamic pixels dynamically is computationally exorbitant.
So how are they physically serving this to maintain a 200 millisecond response time? That's section 4 in the paper, the architecture and latency math.
And the most surprising part is that they did not have to invent a radically new inference engine. The underlying serving topology is actually inherited completely unchanged from v0.2.
They're still relying on that bifurcated system, the thinker module for fast discrete token generation, and the context parallel performer to handle the heavy video latents.
Right. And the performer heavily utilizes Ulysses-style context parallelism.
Which is crucial, because when you generate high-resolution video latents sequentially, the context window explodes in size instantly.
Exactly. The memory required for the key value cache becomes a severe bottleneck for a single GPU. Ulysses parallelism shards the sequence dimension across the GPU cluster's tensor parallel domain.
It swaps representations via all-to-all communications.
Yes, so each attention head only computes on a fraction of the sequence, distributing that massive attention computation without choking the single-chip memory bandwidth.
And all of this operates on a unified causal timeline. Language, audio, and video all share this timeline, coordinated by block causal attention. But they use different generation paradigms under the hood, right?
They do. The discrete elements, the language, and those parenthesized behavior directives utilize standard autoregressive next token prediction.
But the continuous elements, the dense audio waveforms and the spatial video latents, are generated using conditional flow matching.
Yes, flow matching is critical here. Standard diffusion requires traversing a really curved, highly complex trajectory from pure noise over many iterative sampling steps. Flow matching constructs a straight-line vector field.
Which allows for much faster ODE solvers during inference.
Right, requiring significantly fewer steps to generate high-fidelity latents. That straight-line trajectory is an absolute necessity for surviving the real-time latency budget.
And the text tokens generated by the thinker act as a highly compressed explicit conditioning signal for that flow matching process. Which brings us to the hard numbers. The streaming unit, the discrete chunk of time processed in a single forward pass, is 160 milliseconds.
And the model-side response latency sits tightly at approximately 200 milliseconds.
When you factor in a generous 350 millisecond bidirectional network budget for data transfer, the total interaction latency for a full duplex, visually grounded, open vocabulary response is about 550 milliseconds.
That is well below the threshold where human conversation starts to feel awkward or delayed.
Let's synthesize the systems engineering brilliance of this, because it is essentially a massive conceptual hack. The genius isn't that they brute forced a heavier architecture to handle physical behavior.
Not at all.
Because the behavior directives, like takes a sip of water, are just a handful of standard discrete language tokens. They add virtually zero computational overhead to the thinker module.
Exactly. Generating 10 text tokens is computationally trivial. They basically unlocked open vocabulary video generation for free in terms of latency.
Because those cheap text tokens act as rigid guardrails, keeping the speech, behavior, and visual appearance perfectly synchronized in latent space long before the expensive flow matching even begins.
By reframing the fundamental problem as a persistent world plus a dynamic event stream and using natural language to bridge them, they entirely bypass the latency penalty of heavy cascaded pipelines.
Which leaves us with a highly provocative thought to mull over. If Wan-Streamer v0.3 proves definitively that a unified transformer can treat a pre-filled world KV cache as a separate variable from a real-time event stream,
and physically manipulate that world using natural language tokens without breaking a 200 millisecond latency budget.
Exactly. What happens when we step outside of the avatar chat interface entirely? We are no longer looking at a blueprint for a better virtual assistant on a screen.
We're looking at a foundational systems architecture.
Right, where the world context could be real-world robotic sensor data, LiDAR scans, or the physics engine of an open-world game. This paper proves a single multimodal pipeline can allow an embodied agent to reason, speak, and manipulate its surroundings with synchronized sub-second real-time latency. The transformer is built. It is now simply a matter of changing the world data it ingests. Well, thank you for tuning in to AI Paper Slop. We will see you next time.